This video is about singular points. At the outset, we discuss some more points about phase trajectories. The response of a system is shown in the figure. The response is a sinusoidally varying one with an exponentially decreasing envelope. Certain points are marked on the graph with A to H. As far as phase trajectories are concerned, we have seen that it is a plot of x1 versus x2. And for traditional systems, these can be treated as y and y dot, where y is the output and y dot is its derivative. So here also, let us assume that we are plotting the phase trajectory y and y dot. The response is given as y. Let us start with the first point. At the point A, we can see that the response has its maximum value, hence the slope is 0. So, let us mark capital A at this point where y is positive and y dot is 0. Now coming to the point B in the graph, B has a value of 0 whereas its slope is negative. So the value of y is 0 whereas its slope is negative. Let us assume that this is the point. Coming to C, we can see that it's a minimum value. So C is negative whereas the slope is 0. So assume that this is the point C. Now coming to D, wherein the magnitude is 0 whereas the slope is positive. So let us take D like this. We can see that if you compare the magnitudes of slopes of B and D, B would be more than D, because as time passes, the signal is attenuated. Hence the slope at D would be less than the slope at B. Hence we can see that this magnitude is more than this magnitude. Now coming to E, it is very similar to A, but magnitude of E is lesser. So it will be a point corresponding to this one. Let us assume like that. Coming to F, it is similar to B, but still a lesser value. G would be similar to C, but with a lesser value. And H would be at the, because there it settles at the origin. Now if you join all these points, we can see that it is going to be like this. And this is what is called the phase trajectory of the given states. Now we can see that the system settles at the point H as time passes. And this response is obtained when we have complex eigenvalues with negative real parts. That is why the system is settling, or it is a stable one. Let us consider another example wherein the eigenvalues are just real and negative. In this case, there won't be any oscillations for the response. We have only an exponentially decreasing response. Let us consider the phase trajectory of this. So in this case, if you plot y and y dot, we can see that at the point A, the magnitude is positive and negative slope. So let us assume that the response starts here. As time passes, we can see that the slope has decreased and the magnitude also has decreased. At the point C, it settles. So the response will be something like this, without a spiral. This helps us in concluding that the nature of the phase trajectory depends much on the nature of the eigenvalues, because eigenvalues determine the nature of the response. Thus we can conclude the eigenvalues determine the nature of the response, which in turn determines the nature of the phase trajectory. We can also see that the response settles to the equilibrium point. Now let us consider what a singular point is. Let us assume that x1s, x2s represents a singular point. If this represents a singular point, then if the system starts at this point, it remains there for all t. It shows that if the system starts at this point, then for all t it remains at x1 of s, x2 of s. So in a way we can say that equilibrium points are singular points. Let us consider a phase trajectory shown here. It starts at x1 of 0, x2 of 0, and as time passes it moves to x1 of t, x2 of t. At any point say p, we can find the slope of this phase trajectory by drawing a tangent line whose slope is given by delta x2 by delta x1. So we can call the slope as delta x2 by delta x1. This can be written as dx2 by dx1. We can rewrite this as dx2 by dt by dx1 by dt. This is nothing but x2 dot by x1 dot, which shows that capital N basically depends on the system equations. x2 dot and x1 dot are the state equations of the state model. Hence the slope depends on the state equations. This is how we say that the state trajectories depend much on the behavior of the system. At singular points we can say that since the system states have no change, x1 dot equal to 0 and x2 dot equal to 0 holds good, which shows capital N is equal to 0 by 0, which is indeterminate. It is this indeterminacy of the slope accounts for the term singular. In a phase plane, when you draw a phase trajectory, at the singular point, the slope of the phase trajectory is indeterminate. Let us consider a linear equation x1 dot is equal to x2 and x2 dot is equal to 2x1 plus 5x2. At the singular point, x1 dot is equal to 0. Hence we can say x2 equal to 0. Simultaneously, x2 dot is also equal to 0, which gives the solution from the second as x1 is also equal to 0, because we have already obtained x2 equal to 0. So we can say that 0, 0 is the singular point. As far as the linear system is concerned, there will be only one singular point. This is very clear from this example. We don't have any other solution that says x1 dot equal to 0 and x2 dot equal to 0 simultaneously. Hence we can conclude for linear systems we have unique singular points. Hence the phase trajectory for linear system also will be unique. Here are some points to be noted. Singular points are equilibrium points in the state space. We have seen that equilibrium points are points where the system settles. At singular points, the states do not change. Hence, equilibrium points are singular points. We have also seen that linear systems have unique equilibrium point. The solution for x1 dot equal to 0 and x2 dot equal to 0 simultaneously occurring would be a unique value. But for nonlinear systems, we can see that they have multiple equilibrium points because of the very nature of the equations. There could be more than one equilibrium points for nonlinear systems. As mentioned before, the nature of the singular points depend much on the nature of the eigenvalues. So from the point of view of the eigenvalues, we have certain classifications for the nature of the singular points. We consider here a second order linear system. If the eigenvalues are both positive and real, we call the singular point as an unstable node. The unstable occurs from the fact that the eigenvalue is positive, and the term node occurs from the fact that the eigenvalue is real. And if you have both the eigenvalues as negative and real, we have a stable node. Suppose that one is positive and the other is negative, we can say that it is a saddle. If the eigenvalues are complex with positive real part, then we have an unstable focus. So the term focus occurs from the term complex. If the eigenvalues have negative real part and complex in nature, then the singular point will be termed a stable focus. If the eigenvalues are complex with zero real part, then we call the singular point as a center or a vortex. The graphical description of these singular points and the corresponding phase trajectories will be discussed in the upcoming video. Thank you.